In this section, we will consider the different types of sequences and the rules that are used to generate them. Take a moment to consider what the rule would be for each of these sequences. So hopefully you will have spotted that the first sequence we are dividing by 4 or multiplying by a quarter to get the next term each time. For the second sequence, we are adding 1. For sequence 3, we are subtracting 3.5 each time. The next sequence, we could consider that we are multiplying each term by 2 to get the next term. For the next one, we are dividing by -3 or multiplying by -1/3. You can see that this gives the effect that the sign alternates, plus minus each time. For this sequence, we can see that we are multiplying by 3/4 or multiplying by 3 and dividing by 4. And the final sequence, we are adding 2 each time. So we basically have two types of sequence here. We have the types where we are adding or subtracting a number to get to the next term, and we have the ones where we are multiplying or dividing to get to the next term. We're going to consider each of those two cases separately. So first we're going to look at arithmetic progression. This is where a sequence is formed by adding a constant number onto the previous term to get to the next term. We sometimes shorten arithmetic progression to AP. So its recurrence relation is quite a simple rule. It's UN plus 1 equals UN plus D. In other words, to get to the next term, take the term before it and add on a constant D. We use the letter A to denote the first term when we are considering this algebraically, and we use the letter D for the common difference. If D is a negative, this means that the sequence will be decreasing. If D is positive, it means the sequence will be increasing. So we're going to calculate what the first few terms would be using A and D. You may want to pause here to fill in the table. So the first term is A, and then if we add a common difference of D each time, we get a second term of A plus D, a third term of A plus 2D, and a fourth term of A plus 3D. Consider what the rule would be for the nth term. So for any term in the sequence, how would we calculate it using A and D? You may have noticed that the coefficient of D is always 1 behind the term number that we are on. So UN, the nth term, would be A plus n minus 1D. So this gives us our first rule, which is that UN equals A plus n minus 1D, where A is the first term, D is the common difference, and n is the term number that we want to find. This isn't given in the formula booklet, so you do need to learn it. This could be used, for example, to find the 10th term. The 10th term will be A plus 9D, and so on. An arithmetic series is the sum of a certain number of terms in an arithmetic sequence. So for example, we might choose to add up the first 10 terms. We use Sn to denote the sum of the sequence or the series. So for example, if we start with an arithmetic sequence 4, 7, 10, 13, 16, the sum of the first 5 terms would be 50. In this case, S5 would equal 50. Again, we're going to fill in a table using A and D to find the general formula. You might want to pause here and fill it in yourself. So we know that the sum of the first one term is just the first term, which is a, and the sum of the first two terms will be a plus the next term, which is a plus d. This adds up to 2a plus d. We're now going to add the third term onto this to get the sum of the first three terms. We're adding a plus 2d, which is the third term, so we get 3a plus 3d. To add the fourth term, we're going to add a plus 3d, so we get 4a plus 6d. Now you may be able to spot a pattern emerging looking at the coefficients of a, they're going up by 1 each time, and the coefficients of d, which seem to be going up by different numbers each time. This is the rule, so we have na and then a half times n minus 1 d. So we can find the sum of the first n terms of any arithmetic series using this formula. We can factorise the formula that we had in the table on the previous page. If we factorise out a half and an n, this simplifies to give us Sn is a half n bracket 2a plus n minus 1d. This formula is given to us in the formula book, and if you know what the last term of the sequence is, if we know that there are n terms, we know that the last term will be the nth term, which is a plus n minus 1d. So we can use one of the a's from here and the n minus 1d here and replace that with L for the last term. So this gives us 1a plus L in the bracket, or half n a plus L. This isn't used as often as we usually don't know what the last term is unless we calculate it separately. So both of these formulas are given to us in the formula booklets. If we know how many terms we want to add up and we know the first term and the common difference, we can find the sum of the first n terms in that series. I'm going to introduce the idea of sigma notation. Sigma notation is a shorthand way of writing sums. We use the Greek letter sigma. This is a capital S in Greek and it stands for summation. So a series written in sigma notation might look something like this. I'm just going to go through each of the parts to explain what they all mean. So here we have the rule that produces the series, 2n plus 1. We could write this as 2r plus 1 or use any other letter really there for instead of n, as long as the letter here matches the letter that is used here. It doesn't actually matter which one we use, but n and r are quite common in these questions. The number at the bottom of the sigma tells you where to start in your substitution. So for example, when we substitute in n equals 1, we get 2 times 1 plus 1. We're then going to continue substituting in the next number. So substituting in n equals 2 would give us 5, 2 times 2 plus 1. Substituting in n equals 3 gives us 7. Substituting in n equals 4 gives us 9. And then the top number tells us when to stop, what is the last number to substitute into the formula. In this case 5, 2 times 5 plus 1. So here we have the first 5 terms starting with n equals 1, ending with n equals 5, and we are adding them up because the sigma is telling us to do so. So we get 3 plus 5 plus 7 plus 9 plus 11. This adds up to 35. There is also a summation button on the calculator. You may be able to find this. It's in yellow just above the X button, which is just below the on button at the top. So here, for example, if we wanted to find S10, we could calculate the sum from n equals 1 up to 10 of the function f. Fn would just be the rule for the series. However, this notation means that we have to start with 1 as our first number to substitute in. S10 has to mean the first 10 terms, so starting with 1, finishing at 10. It might be, however, that we want to find a summation that doesn't start with n equals 1, so we have to use a rule for this. For example, we might want to start with the 4th term in the sequence and add up the 4th, 5th, 6th, 7th, 8th, 9th, and then finish with the 10th. In this case, you can see the number of terms we are adding up, 4, 5, 6, 7, 8, 9, 10. We're actually adding 7 terms up here, so just be aware when calculating these sums that the number of terms is the top number minus the bottom number, but then adding on 1. So we can do this by first of all calculating the sum as if it was the sum from 1 to 10, which we can use our rule for in the formula book. Then we need to subtract the terms that we don't want to be included. So if we are starting with term number 4 and adding up 4, 5, 6 and so on up to 10, the 10th term, we don't want to include term 1, term 2 or term 3. So we would need to subtract this from the sum. Therefore, if we want to find the sum starting with n equals 1 and ending with n equals 10, we could find the sum from 1 to 10 and subtract the sum from 1 to 3. This takes away the first 3 terms. This could then be calculated using the rule from the formula book using S10 minus S3. Notice here that this number is the same as the number at the top, but this number is always 1 less than the number at the bottom because we want to include the number at the bottom, so we want to take away the sum of all the terms before that. So we're now going to consider this example where we have an arithmetic progression and we want to find the 8th term and also the sum of the first 6 terms. We've got formulas that we can use for both of these. So to find the 8th term, we're going to use the nth term formula, which was un equals a plus n minus 1 d. We can see from the sequence that a is 18, that's the first term, and d is minus 5 because the terms are going down by 5 each time. We're going to use n equals 8, which means that n minus 1 will be 7, so a plus 7d. When we substitute these numbers in, we get that the 8th term, u8, is 18 plus 8 minus 1 or 7 times minus 5. This gives us negative 17. To find the sum of the first 6 terms, we can use the formula from the formula book, which is Sn equals a half bracket 2a, a half n bracket 2a plus n minus 1 d. We're going to put in n equals 6, a equals 18, d equals minus 5. Substituting these in gives us the sum of the first 6 terms as 33. We're now going to consider this question, which uses sigma notation. We need to be careful because we can see that the summation doesn't start with n equals 1. It starts with the 5th term and adds up the terms until we get to the 15th term. There are several ways of tackling this problem, so we're going to look at a couple of different ways of doing this. So the first thing we can do is we can say if we want the sum from the 5th term to the 15th term, this would be the sum from the 1st term to the 15th term, but then we don't want the first 4 terms because we want to start with term number 5. So we could then subtract the sum from n equals 1 through to 4. The rule for both of these is the same as the rule in the question, which is 46 minus 3n. We can now consider what the first term and the comma difference would be for the sequence 46 minus 3n. So if we substituted in n equals 1, 46 take away 3 times 1 gives us 43, and substituting n equals 2 gives us 46, take away 3 times 2, which is 40. So we can see that this sequence goes 43, 40, and so on. So the series has A is 43, that's the first term, and D is minus 3 because the terms are decreasing by 3 each time. We can now see that this sum will be S15 take away S4. This is from here. This is S15, the sum of the first 15 terms, and this is S4, the sum of the first 4 terms. We can use the formula for Sn from the formula book, a half n brackets 2a plus n minus 1d, substituting in n equals 15 and n equals 4. So substituting in n equals 15 gives us this, along with the a and d values from above. Substituting in n equals 4 gives us this. So this gives us a sum of the first 15 terms is 330, and the sum of the first 4 terms is 154. So the sum of the terms we want from the 5th to the 15th term must be 176. So that was one method of calculating that summation. Another method may have been to use the other formula in the formula book, Sn equals a half n a plus l. We would need to be careful here to make sure that we were using the correct values for a and l. It wouldn't be the same value a that we calculated earlier, because in this case we would want to use the first term as being term number 5 in the sequence. So a would be calculated by putting in 5 in here, 46 take away 3 times 5. So we could substitute that in. This would give us that a is 31. We could also substitute in d. D would still be minus 3. We can see here that the terms are going down by 3 each time. We'd also need to use n as being how many terms there are. If you start at term 5 and go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, you have counted 11 terms there. So n would need to be 11. So an alternative way of calculating this will be using n equals 11, a equals 40, 31, and L would be calculated by substituting in 15. So 46 take away 3 times 15. So had we expanded this out, we would have ended up with a sequence starting at 31. This would have given us different values for a and n, but it will have given us the same answer, 176. Now we're going to consider a problem involving ticket costs. Imagine that there is a concert where the price of a ticket increases each day as we get closer to the day of the concert, starting with the first day of the month. We are going to model this using an arithmetic progression, so assuming that each day the value of the ticket goes up by the same amount every time. And we are told the following information. We are told that if you bought a ticket every day for the first 25 days, starting from the first day of the month, the total cost would be £3,500. And we are also told that if we bought a ticket on just day number 5, you would spend £100. From this, we want to find how much the ticket was on the first day and how much it was increasing by every day. So the first piece of information, we are told that if you bought a ticket every day for 25 days, this would be the sum, this would be S25, so the sum of the first 25 days. So we could use the formula, a half n 2a plus n minus 1d. We can see here half n is 12.5, that's half of the number of days, half of 25. Then we've got bracket 2a, we don't know what a is yet, plus n minus 1, which is 25 minus 1 times d. So that is the formula for Sn. We know that that sum of 25 tickets is has a total cost of 3,500. This simplifies slightly, so we can divide across by 12.5 and then divide everything by 2 to give us an equation 140 equals a plus 12d. We're now going to use the second piece of information to find another equation. So we're told the cost of a ticket on day 5. This is just the 5th term. We know that the formula for the 5th term is a plus n minus 1d. So this will be a plus 5 minus 1d or a plus 4d. This is £100, so we have 100 equals a plus 4d. We can now solve the simultaneous equations that we have. We have a plus 12d is 140 and a plus 4d is 100. You can either solve this by hand or you can put it in the simultaneous equation solver in the calculator. This leaves us with a is 80 and d is 5. So this is telling us that the initial ticket cost on day 1 was £80 and it increased by £5 every day. Now complete exercise 3.1 on page 294. We're now going to consider geometric progressions. A geometric progression is a sequence that is formed by taking the initial value and multiplying by the same number each time. So there is a common ratio between each of the terms. We sometimes call a geometric progression a GP. The recurrence relation for this would be un plus 1 equals r multiplied by un, where r is the common ratio that we multiply each term by to get the next term. We still use the letter A to denote the first term of the sequence, but we use r for the multiplier, for the common ratio. So we're going to complete this table to work out the terms in terms of A and R in this sequence. So the first term we know is A, and the second term is A multiplied by R. The third term is the second term multiplied by R again, so this gives us AR squared. The fourth term is then the third term multiplied by R, which gives us AR cubed. So we can spot here that the power of R is always 1 behind the term number that we are on. So to get the nth term, we calculate A times R to the power n minus 1. For example, the 10th term will be AR to the power 9. So we can find any term of a geometric progression using this formula. Un equals AR to the power n minus 1. This is not given in the formula book, so you do need to learn this one. So a geometric series is the sum of the first n terms of a geometric progression. So Sn can be calculated by finding the first term plus the second term plus the third term all the way up to the nth term. So this would be written as A plus AR squared and so on, all the way up to AR to the power n minus 1. We're going to try to simplify this into a formula that we can use. So we're going to start by multiplying both sides of this by R. So the reason we have done this is so that we can subtract one from the other. If we take the first line and subtract the second line, the left-hand side becomes Sn minus R times Sn. However, the other side, a lot of the terms are going to cancel out. For example, we have AR here, and when we subtract AR, that will cancel. We also have AR squared, which will cancel with this minus AR squared here, and so on. Nearly all the terms are going to cancel in this manner. There's going to be a few left over that don't cancel. This A won't cancel because there isn't an A here to take away. And similarly, we don't have an AR to the n on the first line, so we will still have minus AR to the n on the end here. We can now factorise this. So the left-hand side has a factor of Sn, so we can pull this out here, Sn bracket 1 minus R. The right-hand side has a factor of A, so we can pull the factor of A out here, leaving us with 1 minus R to the n. Finally, we want a formula for Sn, so if we divide by the brackets here, 1 minus R, we're left with this formula. Now, you don't need to be able to derive this, you are given it in the formula book. This is the sum of the first n terms of a geometric progression. So this formula here, Sn equals A bracket 1 minus R to the n over 1 minus R. This is given in the formula book, you don't need to memorise it, but you do need to be able to use it. So we're going to take this geometric progression and calculate the 8th term and then the sum of the first 6 terms. So to get the 8th term, we're going to use the nth term formula, which is un equals ar to the n minus 1. This means the 8th term, u8, will be ar to the power 7. We can see the first term is 135 quite easily. To find r, it's not always obvious what we are multiplying by, so the easiest way to find r is to take any term and divide it by the one before it. For example, 45 divided by 135, or 15 divided by 45. This, in both cases, gives us 1/3, so r must be 1/3. So substituting this into the formula gives us u8 is 135 times 1/3 to the power 7. This is a decimal, so there's 3 significant figures. The 8th term of this geometric progression is 0.0617. Now to find the sum of the first 6 terms, we can use the formula from the formula book. Sn equals a bracket 1 minus r to the n over 1 minus r. If we substitute in a equals 135, r is 1/3 and n is 6. This gives us a sum of 202 and 2/9, or a decimal equivalent of that. Now complete exercise 4.2 on page 297. We're going to start this next section with 2 options to consider. Which of these would you pick and why? Option 1 is that you can start with 2 pence today, and the next day you'll be given double that amount. The next day you'll be given double that amount again, and so on, with the pattern continuing forever. The alternative is that you could start with £50,000 today and be given half of that amount tomorrow, half of that again the next day, and again continuing forever. We'll come back to that at the end to decide which of these might be the best. So we're going to use some of these, the formulas from the previous section to calculate some of these values. In each case we have geometric progressions. We want to calculate what the value of r would be, the common ratio, and then find the sum of the first 5 terms. We're also going to find the sum of the first 20 terms. We can use the formula for the sum in the formula book for both of those. Then we're going to consider what would happen if we continued adding up these terms forever. In other words, what would the sum up to infinity be? You might want to pause the slide here and fill in as much of the table as you can. So filling in some of these values, we can see the common ratio each time. We have 1/4, 2, 3, 3/4, 1.1 and minus 1/3. Remember that to find the common ratio, if you take any term and divide it by the term before it, in a geometric progression, this will give you the common ratio. To find S5 and S20, you're going to use the formula for Sn, which is in the formula book, using n equals 5 for the first column and n equals 20 for the second column. You can use a as the first term in each of the sequences and r as the common ratio. So here are the values that we get. Now, if you continue calculating these, you will find, we'll see why this is in a minute, but you'll find that the sum up to infinity of the first one is 106 and 2/3. In other words, adding on the terms forever will give us a sum that gets closer and closer to this value, 106 and 2/3. The second series doesn't have a limit. As we keep adding on more and more terms, because the terms that we are adding on are getting bigger and bigger and bigger, there is no limit, it just tends towards infinity. This is also true with the third. The fourth, if we continue adding on more terms, the terms we are adding on are getting smaller each time, and this tends towards a limit of 32. The next progression, Again, doesn't have a limit. As we keep adding on terms, the sum tends towards infinity. And the final progression gives us a limit of about 11.25. In a geometric progression, there are two possibilities for what will happen to the terms as n tends towards infinity. The first is that the terms will get smaller and smaller and tend towards zero eventually. The second is that the terms keep getting larger and larger, and in this case, the terms tend towards infinity. If we are in the situation where the terms are tending towards zero, then we will call this a convergent sequence because the values are converging on a limit. In this case, they are converging to zero. If we're in the situation where the terms are tending towards infinity, we call this a divergent sequence because the terms are not tending towards a limit. And the thing that dictates which of the two situations we are in is the common ratio. If the common ratio is between -1 and 1, then the terms will be getting smaller and smaller each time, and therefore the sequence is converging to zero. If the common ratio is either greater than 1 or less than -1, then the terms will be diverging. Notice that if the terms are negative, they'll be diverging, but also oscillating between positive and negative. If we are in the situation where we have a converging geometric progression, where the terms that we are adding on are getting smaller and smaller each time in the series, that sum is also going to converge because we will get to a situation where we are adding on numbers that are very close to zero. This series will converge on a limit, and we call this limit the sum to infinity. In other words, if we added up all of the terms forever, then the sum would get closer and closer to this number. We know that the sum of a geometric series is given by this formula. If we are in the situation where r is between -1 and 1, then the r to the n term on the numerator will tend towards zero as n gets larger. So therefore, we are left with just a times 1 on the numerator. So the sum to infinity formula is a over 1 minus r. This only works when the absolute value of r is less than 1. In other words, the value not taking into account the plus or the minus is always lower than 1. This formula for sum to infinity is also given in the formula book. So we're going to go back to this situation here and decide which option we would pick and why. As we can see, these are both geometric progressions. Option 1 has an r value of 2 because although we are starting with 2 pence, 0.02 pounds on our first day, we are multiplying by 2 every time. So therefore option 1 will increase without limits, and if this continued forever, then we would end up with an infinitely large amount of money. Option 2, however, has an r value of 0.5 because each time the value is divided back by 2. So therefore, there will be a sum to infinity. You can calculate this by using a as the initial value on day 1, 50,000, and using r as 0.5. So the sum to infinity you can calculate will tell you how much money you will end up with eventually. So theoretically, option 1 is the better one because this has no limits. However, you may want to consider the amount of time it will take for option 1 to overtake option 2 before you choose your final option. Now complete exercise 4.3 on page 298.